First of all, I would like to thank you very much for the invitation to give a talk here. I will talk about joint work with Annalena Kieslinger, also from the University of Erlangen and Nuremberg. As an outline, I try to introduce today a new, quite far-reaching and flexible toolbox of distances, divergences, disparities, similarity measures between probability distributions, but they all can be done also for non-probability distributions. That means non-negative functions in fact. As already Michel mentioned, I will extract several important widely used distances as special cases, and at the end I will show you some general asymptotic distributions for data-derived divergences, which, for instance, can be used for goodness of fit testing. So, of course, everyone knows here how important divergences or similarity measures are between probability distributions and also non-probability distributions. They are used in statistical inferences all over the place, parameter estimation, etc., etc., and of course also in machine learning, information theory, signal processing, etc., etc. So, how to measure the closeness between two, for today, probability distributions? So, which divergences are available? So, of course, let us mention very prominent examples used very often. Of course, the Kullback-Leibler information discrimination, or also named relative entropy. Then, of course, also the Hellinger distance, Pearson chi-squared, you can see, Pearson chi-squared divergence. Then, of course, also total variation distance. And they are all covered by the more general class of Chissa, Ali, Silvey, phi divergences. And another class of very important divergences are, for instance, the squared L2 distance, density power divergences, and they are covered by the more general class of ordinary classical Bregman distances. So today, all these examples will be covered by the much more general context, and it's driven from the desire to have a toolbox of a whole class of divergences, and which is far-reaching and flexible, and this for today will be reflected by different choices of a so-called generator phi of the divergence, and I will also introduce three different kinds of scalings. So, for notation, so we want to measure for today the distance between probability distributions P and Q. And they are supposed to have a density, small p and small q, with respect to some reference measure, and then I have three scaling measures, which typically are non-probability distributions. So they are finite or sigma finite measures. Of course, if the reference measure is the Lebesgue measure, then all these functions P, Q are classical densities, and M is a classical non-probability density. And if the reference measure is a counting measure, then P and Q are nothing else but probability mass functions or counting densities, frequencies, and the M's are non-normed ones. Okay, so how about the generator for the divergence? So, if you, always think that phi may be, for instance, strictly convex, okay? But today I will also introduce a more general context based on the, of course, well-known concept of abstract convexity. So we take phi to be the generator, and then we take a class U of functions, which are supposed to be lower approximating functions, so potential lower approximating functions. Typically, of course, the family U consists of functions which are less complicated than the generator itself. Okay, then a function U is called a strict subgradient basically, of course, it has to be of the class U, and basically one is satisfied. So the set of all the strict U subgradients is called the strict U subdifferential, of course, always at the point y0, and we denote it like this. Okay? So, on the other hand, a function phi is called U-convex if it's basically, well, if phi at the point y is the supremum over a U function plus a constant. Okay? And of course, this part here always has to be lower than phi. So in a sense, it's a kind of a lower envelope. So for today, we assume that the generator of the divergence is U-convex and has at least one strict U subgradient at each point. So the subdifferential is non-empty for all points. Okay? Then you can rewrite the equality which I've just shown. You can replace the sub by the max. And if the class U itself is invariant under addition of constants, then you can forget about the C, of course, and then it just gives you the representation that phi is at the point y is nothing else but the maximum of all curved lower envelopes at y. So, of course, this is a special case. If U is the class of all affine linear functions, then phi, the class phi is the class of all strictly convex functions. So, here is our new divergence. So, we want to measure the distance between the two probability distributions P and Q, and I have two scaling measures, M1 and M2, and I have an aggregating measure called M3. And here's our distance. So first, look at, so we take a subgradient U, okay, well, we look at all subgradients U at this point, so the second density scaled by the second scaling density, okay, and then we take this term here, so this deviation here, okay, so it's a deviation between phi at this point and this function U also at this point, okay? So it's an aggregated pointwise deviation between generating function and the lower envelope touching at this point Q divided by M2, okay? I will do this for each x and then I aggregate it, okay? Of course, you can do it if you replace P and Q, the probability measures, also by non-probability distributions. That means general non-negative functions, okay? So, well, it's always by construction less or equal, greater or equal to 0, and it is proper, as we say. Okay, so in the discrete setup, we have the counting measure, and then the integral turns into a sum. Okay. So now I will hierarchically draw down subclasses, sub-subclasses, etc. So the first special case is if the generator is decomposed, it is composed by a strictly convex, a strictly increasing function h, and a strictly convex continuously differentiable function phi tilde, okay? If it's of this, and then of course as a kind of lower approximating a class of lower envelopes, potential lower envelopes, I take h of all linear, affine linear functions, okay? And then I end up with this guy here, okay? So, for example, if phi tilde, as I said, is strictly convex and continuously differentiable, and you take h, basically the exponential, then the generator is basically strictly log convex. and then you have this divergence. So, of course, if the H function is the identity itself, yeah, so the generator then is strictly convex and differentiable, then you end up with this divergence given by the equation 6. And if it's non-differentiable, because here there's no infimum, but if there's a cusp, for instance, then then of course you have a left tangent line and a right tangent line, and so you have the distance which is you have to take the distance which is the smaller, of course. Okay, so the infimum comes in here if you have non-differentiable generator. Okay, as a sub class, so to speak, let's suppose that the two scalings M1 and M2 are the same, and I denote it now by ML. L stands for local, okay, local. And the aggregating density should be, again, the local one, but a functional of a global scaling function. So if we take this, then this is the special case. I also changed the notation now, but it doesn't matter so much. So you have this extra term, which can be viewed as a global steepness tuning multiplier and to the generator phi. So you can put it over here, but however, it is non-trivial if this mg depends on the two densities you want to measure the distance between. So it's non-trivial if the choice is adaptive. Okay? So also of course, the local scaling can be of adaptive form as well. So here, going top down, yeah. So we have the sub class, okay, and it's the class of all scaled Bregman divergences. So here, basically the first H term disappears, okay. It's the identity, so to speak, and then we have the scaled Bregman divergences, and the special cases of these are the ordinary Bregman divergences, but also the Chisa-Ali-Silve phi divergences. So for the first one, you choose the identity as a scaling, and for the second one, you choose the second density as a scaling. Okay? And then, of course, a special case of these are Kalbeck-Leibler and Biersen chi-square. So in this context, especially if you have a discrete setup, how can you visualize the scaled Bregman divergences? So here's our generator, the blue curve. And then here you have the states, okay? Then you have the two densities at this state, P and Q, okay? What you do is you scale it, then you get 2 points. Here you take the tangent line, and you measure this distance here. And then you multiply again by the scaling. You do that for every state, and then you sum up, and you end up at the scaled Bregman divergence. But of course, think of the case where M is adaptive, yeah? So they can be highly non-trivial, of course. So, another very important class, subclass, is where H does not disappear, but the scaling disappears, so the M local disappears, and then you end up at the conformal divergences recently developed by Nock, Nielsen, and Amari. And a very important special case of this class, also used in machine learning, is the total Bregman divergences of Liu et al., Benmouri et al., and so on. And here you have the special choice, so the H functional is something like this. Yeah? And the small m is this one. So, as I promised, at the end I would like to show you some asymptotics. Not in a completely general case, but nearly in a completely general case, I take this adaptive point of view for the global scaling and also for the local scaling. And so, first of all, so we have a finite discrete space, okay? So we take the counting measure, all the integrals become sums, and we have a sample, y1 to yn, of sample size n, of a true parametric distribution p theta. Of that we build, as usual, the empirical, so the data-derived empirical distribution, so all the densities are nothing else but the histogram entries, so to speak. And so, of course, the empirical measure will converge in distribution against b theta through. Okay, so this divergence will go to 0, but n goes to infinity. So what is the asymptotic distribution of that? And under, of course, the null hypothesis, that were really the true underlying distribution. And of course, if I knocked this problem, then I can design a Desbus procedure as usual, for goodness of it, for instance. Yeah? So here I need some weak technical assumptions. It's not too hard. So it's just the differentiability of these weighting functions or scaling functions, but they only need to be differential along the diagonal, not everywhere. Okay. So here's our theorem. Of course, I will not comment on that in detail. The point is we get something without more or less no assumptions other than these technical assumptions. I don't want to go through the formula. The message is that the asymptotic distribution is a mixture between standard chi-squared distributions, I mean the squared of standard normal distributions, but the weights depend on the parameter in general. Okay, so two comments, that this theorem covers also the conformal divergences and also the total Bregman distances, and maybe Frank can tell us, I don't think that there exist asymptotic results for conformal divergences yet, so this is new. And this theorem also generalizes a theorem which we had last year in a paper for scaled Bregman divergences. And of course, it is an important question to ask whether the asymptotic distribution can be parameter free. In this case, it would be just plain chi-squared. The answer is astonishingly general. So there are two special cases. In uniform distribution, it always holds, no matter which divergence I choose, which is important if I want to test my random sampling scheme. In the Kalber-Gleiber divergence, but this is known, of course, it's also independent. And in all cases where I have this diagonal assumption, so that means V is classical density. So this classical is the density at P, and here is the density Q. So if they coincide, it should give you exactly what you want. That's the only condition we need. And then you get chi-squared. So it's very, very general. But in the unscaled case, like it is with the conformal divergences, for instance, then the limiting distribution is parameter dependent. Okay, so to sum up, so I introduced you a very far-reaching and very flexible toolbox of distances, divergences between two non-probability distributions, and I gave you a lot of well-known distances as special cases, and at the end I showed you some asymptotic distributions for data-derived divergences, which can be used for testing and machine learning whatever you like. So here I would like to end my talk, and thank you very much for your attention.
Remarks, questions,
Thank you very much for the nice talk. Do you have any idea of what kind of axiomatic properties this novel class of divergences can have? For example, for Caesar divergences, we know information monotonicity.
Okay, yeah.
Do you have such kind of idea of how it comes?
It's a very interesting question, and of course, since everything is very general, it means a lot of work. We have not so far looked upon it, but it's a very important question. Of course, there's a similar scheme also for the power divergences and stuff like that, Salis and also things like that. So it has to extend these things.
Because
So, yeah, of course.
I remember some paper by Lisa on how condition when the Weber row divergence is Caesar 1 or Rayman 1.
Yes.
So did you try to play with
Not yet. I mean, we have to do one thing after the other, but it's a very good question, very important question, and so maybe let's do it together and to apply it to machine learning also.
other questions, remarks?
Just one question about you are mentioning all around your speech the fact that you have let's see. You are mentioning during your speech the fact that you are measuring a behavior which is like a chi-square, etc., at certain moment of your demonstration. Okay? But there exists another criterion as a limit for a lot of measurement constraints, which is called the Janssen-Berzelius measure, which is asymptotically equivalent to a chi-square, and which is separable, like your approach. Have you tried something around this idea?
Well, the idea of the proof is to make a Taylor expansion to the second order, and then to show, in a sense, asymptotic equivalence to the chi-squared, and then, well, at least in the case where, the last case where we, where the, yeah, okay, and
This the goal of my question is the fact that you are.
in the last case here, you can really proceed, and it's really asymptotically equivalent to the chi-squared, and then you can use the result on the chi-squared.
My question is there is another criterion, not as chi-square, but something which is a little bit different, which is more closer than your approach, which is based on the Janssen-Berzelius measure.
Yes, I have not looked at this yet.
Can you obtain the raw tau divergences of Zhang as special tests?
Maybe, yes. We haven't looked at it because, you know, it's really a zoo, a jungle, so you have to start step by step, you know, and I try to do it in a hierarchical way, I think, but...
Thank you very much. Thank you very much for this talk.